So this is basically just going to be a rundown of all of the stuff I talked about in the last 3 videos. So the way this reflecting laser works is that this is a painting that goes off into space. When it hits something, the painting cuts off at the reflection point, and it teleports a different laser segment to that position that's pointing in the direction that is accurate to like the reflection. So how do we do that? Well, we have a laser scope that's there to detect that it is going to reflect off something. And then using the direction of the laser and the surface orientation, we calculate the reflection, which happens here. And then we pass that into the next laser segment and set the position and orientation using a follower and a lookout rotator. Alright, so here's what we got to work with. We have the laser, which is represented by this red vector. We have the direction the laser is pointing in, and we have the direction the surface is pointing in with this green vector. So we need to do a bunch of math to basically get, this vector that's just completely flipped over this surface normal. So how do we do that? Well, first thing, I guess, the easiest thing we can do is just flip the direction of this vector, right? Because our result is going to be pointing away from the surface, not towards it. So it makes sense to flip it first. And then we want to flip this over the surface normal like this, right? So how do you flip something over something else? Well, you're basically taking the amount of it that's parallel to this and keeping it the same, and taking the perpendicular amount and flipping that. What we need to do is break this into its parallel and perpendicular component relative to this, and then flip the perpendicular component and then recombine them. So if you saw the last video, that means we're probably going to be using the dot product. One thing to note is that the surface orientation and the screen space direction from the lookout rotator are both already unit vectors. The length is already 1. So that means if we're dealing with dot product at all, we know that the value we get from the dot product is going to be like exactly this length. If we take that dot product amount and we multiply it by the surface orientation, we get the parallel component. Like this. We'll make that blue. So this is the parallel component. And then if we subtract the parallel component from this laser direction, we get the perpendicular component. So now that we have the parallel and the perpendicular component, all we have to do is multiply this by -1 to make it keep the same length but flip its direction. And then we add these two back together, and that gives us this, which is the reflected vector, which is exactly what we need. Alright, so if we follow all of those same steps through Dream's logic, then we get what we have here. Multiply the incoming vector by -1, get the dot product of both, which again, this was the thing made by Fort. The dot product gives you the length, so you multiply by the surface orientation to get the actual vector. You subtract the incoming vector by its parallel component to get the perpendicular component. Then you flip the perpendicular component by multiplying by -1, and then you add it back together with the parallel component. And that's what gives you the nice reflection. Alright, well, anyway, so that was a whole bunch of stuff about vectors in Dreams, but it's also stuff that can be carried over to if you go and do any sort of game programming. Just knowing what a vector looks like and how it can be manipulated and that kind of stuff. Getting comfortable with that is a really useful skill when it comes to like making gameplay. So hopefully all this stuff helped. Hopefully it wasn't too confusing. And hopefully you learned stuff. Yeah, see you around.